Right, so here we have Griffiths Electrodynamics, problem 2.6. We're going to be looking this time at a solid disk of charge and our good old point P, which is a distance z straight up from the middle of it. All right, so this time we're dealing with a surface charge density we call sigma. Now there's a couple ways to do this. You could use the result of the previous problem, where we did a ring and then have a whole series of rings that you integrate out. I'll just do it the way of using an area integral. So the electric field, right? If I didn't say before, that's what we're finding, the electric field at this point P due to this this disk of charge. All right, so the electric field is given by 1 over 4 pi epsilon naught, and we integrate over the charge density, which in this case is sigma. We could put this little r prime thing. We don't need that again because sigma will be constant over this disk, so we can just have sigma here. And downstairs we have our cursive r squared. We have our cursive r hat vector, and this time we have a differential area. We'll call d sub a, or just dA, sorry. Prime. We use the primes for the source points, and the unprimed for the field point. So breaking this down into pieces, let's just look at this dA real quick. So in cylindrical coordinates, dA, it just depends on how far you are out from this origin point. By the way, let's define our directions. Z hat up, and out here is just going to be an r hat. Yeah. Okay. All right, so it's just an r prime times dr. Let's keep the primes on this, times d theta prime. All right. So that, again, the primes mean we're talking about these source points down here, and yeah, so that's it. The distance r out from this center, and then we'll have a theta prime on there around. So our differential area element. All right, like I mentioned before, our surface charge density will just be a constant, sigma, so we can take that right out of the integral. Let's go ahead and look at our cursive r squared. Again, if we were looking at some source point down here on the disk, we draw a line to that source point, and the length of this line is cursive r, the magnitude of cursive r. The direction unit vector from the source point to the field point is this r hat, this cursive r hat. But anyway, this one, this point here is just going to be an r prime. So this is just an r prime. I wrote that really tiny, but r prime squared plus z squared. Okay, and then our hat direction, we're going to take a shortcut here because just like with the ring and just like with the square loop and some of these other problems we've just done for Griffiths, we have symmetry here. So the horizontal components of the electric field are going to cancel out. We get an equal but opposite field contribution from this point over here and this point over here. So all we're going to worry about are the z hat components. So rather than write a unit vector, I'm going to just write the z component of that unit vector, right? So this is kind of awkward, but I'm going to just write r hat sub z, okay? And that is equal to just this opposite, or just this side over the length of the hypotenuse. So we have a z up top, and then the length of the hypotenuse is just the square root of the length squared, right? So this thing under a square root, r prime squared plus z squared under a square root, and then z component, we need a z hat vector. All right, so again, what we're going to look for is just the z component of this electric field, because we know that the horizontal components are all going to be 0. They're all cancel out anyway. So the z component is the only component left at that point. All right, let's put our pieces in. So we've got a 1 over 4 pi epsilon naught. We have sigma, which we're bringing out of the integral because it's constant. Downstairs, let's write out our integral. No, 2 integrals this time, right? Because we're integrating an area. So downstairs, we'll have this piece, and then we'll have the downstairs piece from our hat z component vector. So we get an r prime plus z squared, and this is to the 3/2 power, which we've come to know and love dearly at this point. So we took care of this cursive r squared part. We need this z up top from this, and now we need our dA thing. So we have an r prime, and then we have our I'll write these out here, dr prime, d theta prime. All right, so working outwards in, our theta integral is going to go all the way around the circle, 0 to 2 pi, and our radial integral is just going to go from 0 out to the capital R, which is the outer radius of this disk. So we can do some of this. We have a 1 over 4 pi epsilon naught. We have a sigma. I'm going to bring the z out. Let's go ahead and do the theta integral, because we notice there are no thetas in this integrand. So we just get 2 pi for this theta integral. All right, so 2 pi. And now we are left only with this integral from 0 to big R of r prime over r prime squared plus z prime, and to the 3/2 power, or 3/2 power, that's a 3 over 2, and integrating with respect to dr prime. All right, now we've already done this integral in problem 2.3. It's just a u substitution. What we get is a 1 over, to make sure I translate this into this problem, so 1 over z, and then a minus 1 over r squared plus z squared under a square root. All right, so this integral is just this piece right here. So our final answer for our electric field, oh, by the way, I left off my z hat vector. Let's just toss that in there somewhere. Shouldn't matter where. All right, so we have a 1 over 4 pi epsilon naught. Keep that separate. We have a 2 pi sigma z from this right here. And then we have this 1 over z minus 1 over r squared plus z squared under a square root, like this, and z hat is our direction. So here we go. We've just solved for the electric field up at this point P, which is a distance z perpendicularly from the center of this charged disk with uniform charge density sigma. All right, So Griffiths wants us to take a couple limits and just look at a couple cases and see what we get from it. So suppose, let's do the r is much, much smaller than z first. So what we would expect is that as we get very, very far away from this disk compared to its size of big R, we'd expect it to look like a point charge. What do we find? We get this vector, this electric field is equal to 4 pi epsilon naught. All right, so as z gets very large, this term right here, did I do this right? Make sure I did this right. Z gets very large, z gets very large. Let me just double check this because, yeah, let me double check this. All right, yeah, I did get this sign right. So it turns out that the first term is, anyway, it's going to cancel. We have to expand this. So we're going to just use the binomial expansion. We'll come back to this part in a second. So we've got a 1 over r squared plus z squared, which is equal to r squared plus z squared to the minus 1/2. If we factor out z squared, all right, to the minus 1/2, we get, that gives us a 1 over z up front, and then we have just an r squared over z squared plus 1 to the minus 1/2. Okay, so so because z is much, much larger than r, this term right here is very, very small. And we can use our binomial expansion where this square root of something small is just, something plus the 1/2 of, well, let's just write it out. It's easier to write it out than explain it. And because it's a minus 1/2 here, we get a minus sign in here. So this is, I'm going to write approximately equal to, so we have our 1 over z out front, and then we get a 1 minus 1/2 r squared over z squared. Okay, hopefully I did this right. Okay, so double check. Yeah, I think so. Yeah, okay. Yeah, all right. So now we'll have to move this somewhere else. So coming back to here, we have a 1 over z. So right now I'm just looking at this term inside the parentheses right here. 1 over z, and then minus this stuff in here, which is a 1 over z. So this, the first term in our expansion goes away, which is why we get 0 off the bat. And then a plus 1/2, we have an r squared over z cubed. Okay, so these terms are canceling out, and so I'm just going to plug this thing right here back into where this parenthesis, where inside these parentheses. All right, turned out a little bit messier than I originally planned. Let me switch to a different marker and get better resolution. I don't know. Okay, so we have our 1 over 4 pi epsilon naught. We have a 2 pi sigma z. And then we just have this term here, which is a 1 over 2 r squared z cubed. And again, in the z hat direction. Okay. So what can we cancel out? Well, this z is going to cancel with one of those. These 2's are going to cancel out. Yeah, so we get a 1 over 4 pi epsilon naught. We get our z squared on the bottom. That should make us happy. And then we get a sigma pi big R squared, and all in the z hat direction. So we did recover the point charge because pi r squared is the area of our circle, and sigma is the area of charge density. So this is the total charge of our disk. So total charge, we get our 1 over z squared dependence on the bottom. All right, so last part, we're just going to look at, suppose r is much, much smaller. I'm sorry, larger this time. R is much, much larger than z. What do we expect this time? Well, if we get extremely close to this disk, it will look just like an infinite plane of charge. So we should be able to recover that electric field. Come back up here. Here's our E. This one we shouldn't have to do the whole expansion thing on. This one should be nice and easy. So this time R is going to dominate. Is that right? So we just get basically a 1 over R, and this Z is very small. So we have a 2 pi sigma z, and just double check this one again. Yep, looks like we're on the right track. So we have like we said, R is going to dominate here, and this second term here is going to become very small because R is large and it's on the bottom. So basically, just throwing that term out, we just have a 1 over z, and then in the z hat direction. All right, which just gives us a, this time we will actually cancel out 2 pi. And we'll cancel out the z's. So we get a sigma over 2 epsilon naught in the z hat direction. So we can see that we do, in fact, recover the electric field that we would have gotten from an infinite plane of charge.